Hello everyone, we are starting our technical deep dive into the world of Kubernetes. This session is designed to explain the core concepts of containers orchestration simply and clearly. We will focus on the fundamentals, building blocks, and why this technology has become essential for modern DevOps practices. By the end, you will understand not just what Kubernetes is, but how it fundamentally changed how we manage application at scale. So let's jump in and explain the basic of Kubernetes. Before we define Kubernetes, we need to understand the problem that it solves. Docker is a great for running a single container, but managing hundreds of them manually is simply impossible. The core issue is scale and reliability. If the traffic spikes, manually scaling is too slow and error prone. And if a container crashes, you need a system that automatically detects and fixes that failure. Kubernetes provides the solution by automating deployment, scaling, and the management. It gives us self-healing capabilities and has become the industry standard for the managing containers at scale. This is why we need an orchestrator. Now that we know why we need it, let's define what a Kubernetes actually is. Simply put, Kubernetes is an open source container orchestration platform originally designed by Google. Its job is to manage containers application across multiple hosts and machines. It handles the complex tasks of scaling, load balancing, and ensuring your application are always running. You will often hear it abbreviated as a K8S, which is just a shorthand for the 8 letters between the K and the S. So how does this relate to the Docker? It's important to clarify the relationship between Docker and the Kubernetes because they serve different roles. Docker is the tool that builds and runs the individual containers. It's the runtime focused on a single machine. Kubernetes, on the other hand, is the orchestrator. It manages those containers across an entire cluster of machines. Think of Docker as an engine that powers the car. Kubernetes is the GPS and the traffic control system that direct a fleet of those thousands cars. They work together to achieve the simple goal, running your application reliably. Now look at how Kubernetes is structured. To understand how Kubernetes works, we need to look at its high-level architecture. A Kubernetes cluster is simply a set of machines working together to run your application. This cluster is divided into two main parts. The control plane is the brain of the operation. It manages the cluster and schedules where containers should run. The worker node are the muscle. These are the machines that actually run your application workload. We will dive into the specific component of the control plane. The control plane is the brain of your Kubernetes cluster. Make all the global decisions and maintain in the desired state. It is the core set of components that manage the cluster and ensure everything is running as it should. The Kube API server is the front door where communication, internal or external, goes through it. It validates all its requests. All the cluster states, configuration data, and desired state are stored securely in etcd, which is a highly available key value store. Finally, the Kube scheduler decides where new pods should run, and the Kube controller manager runs the background loop that continuously checks the actual state against the desired state. Now that we understand the brain, if the control plane is the brain, the worker node are the muscles where all the actual application workload runs. The key component here is the kubelet, which is the agent running on every node that communicates with the control plane. The kubelet is responsible for ensuring the container described in the pod specs are actually running and healthy on its nodes. Kubeproxy handles the networking side, maintaining the network rules that allow communication from your pods. And of course, we need a container runtime like containerd or CRIO to pull the images and execute the containers themselves. These nodes are where our application lives, and these applications are packaged inside. The pod is the smallest and the most fundamental unit you deploy in the Kubernetes, not the container itself. Think of a pod as a wrapper around one or more containers that need to work together and share resources. The key benefit is that all containers within a single pod share the same network IP and can access the same shared storage volume. This co-location makes them easy to manage as a single application unit, but remember, pods are temporal. They are designed to be temporary and replaceable, which is why we need higher level object to manage them reliably. How do we manage these temporary pods over time? A deployment is the standard way we manage the lifecycle of our stateless application in Kubernetes. It allows you to declaratively define the desired state of your application, such as which container image to use, how many replicas you want running. The deployment controller then works to match the actual state to your desired state. This object gives us crucial feature like easy scaling where we can instantly increase or decrease the number of running pods. The most important deployments enable rolling updates, allow us to update our application version with a zero downtime, and they provide a quick rollback mechanism if an update goes wrong. But even with all these pods running, we still. A service provides a stable network identifier for a set of pods, acting as a constant front end for your application. Since pods are temporal and can die or be replaced, their IP addresses constantly change, which is not reliable for clients. The service solves this by giving you a single stable IP address and DNS name that automatically load balancing traffic across all the matching healthy pods. We have different type of service depending on how you want to expose your application. Cluster IP is the default for internal cluster communication. Node port exposes the service on a state port on every node, and the load balancer provision an external cloud load balancer for the public access. Kubernetes scaling is critical because it ensures your application can handle fluctuation using traffic without manual intervention. We have two main ways to handle this: manual and automatic scaling. Manual scaling is straightforward. You use a simple command to set the exact number of replicas you need. This works well for a predictable workload, but it required human oversight. The real power came from the horizontal pod autoscaler or HPA. HPA automatically monitors metrics like CPU or memory usage and adjusts the number of running pods accordingly. If the load is increases, it scales out. If the load drops, it scales in. This dynamic adjustment is what keeps your application responsive and cost efficient. The self-healing capacities of the Kubernetes are perhaps its most powerful feature, ensuring high availability even when individual components fail. This automatic recovery means the system constantly works to maintain the desired states you need. If a container crashes, Kubernetes instantly detects the failure and restart it, often before any users notice an issue. We use health checks, specifically liveness and the readiness probes, to determine if an application is truly running and ready to serve traffic. Finally, if an entire node fails, Kubernetes automatically reschedules those pods into other healthy nodes in the cluster. Managing application configuration effectively is essential for building portable and scalable application. We need decoupled configuration from the container image itself. Kubernetes provides two primary resources for this: config maps and secrets. Config maps are used for non-sensitive data like environment variables, command line arguments, or configuration files. Secrets, on the other hand, are specifically for sensitive data such as passwords or API tokens. They are stored, encoded, or encrypted within the cluster. The best practice here is always to inject configuration to run using these objects. Never hardcode it on to your container image. Kubernetes is a fundamental tool for the modern DevOps engineering. Directly enable the core principles of continuous delivery and reliability. We use it to deploy applications, managing the entire lifecycle from initial rollout to updates and the rollbacks. It's also central to manage CI/CD pipelines, automating the final steps that push code into the cluster. Scaling application is a daily task, ensuring we meet our user demand while optimizing resources usage. And of course, we rely on Kubernetes to monitor workloads using its built-in health checks and the login to ensure high availability. We have covered the basic of Kubernetes, but now let's focus on how professionals actually use it in production. These are the best practices that ensure your cluster is stable and reliable. First, never create pod directly. You must use deployments to get essential features like self-healing or zero downtime updates. Second, the resources limits are non-negotiable. Setting up CPU and memory request prevents one runaway application from crashing an entire node. Finally, GitOps by storing all your YAML manifest in a version control so you can track every change and rollback easily. Using namespace to isolate environments like dev and prod is a simply way to prevent costly mistakes. We have covered a lot of ground in this module, so let's quickly recap the most important takeaways. Remember that the Kubernetes is the orchestration layer that manages your containerized application across a cluster of machines. The simplest unit is the node pod, which holds your application containers, but you use deployments to manage those pods efficiently. Services are what your application stable networking and the load balancing so user can actually reach them. Ultimately, mastering Kubernetes is now a core skill for any modern DevOps engineer. The foundational knowledge will be essential as you can continue to build out your infrastructure skills. That concludes our module on Kubernetes, but your learning journey doesn't stop here. In the next video, we are going to deep dive into the infrastructure as a code using a Terraform. We will show you how to define cloud resources like servers and networks using simple declarative code. You will learn about providers and the resources and how state management make your infrastructure reproducible, how you build and manage cloud infrastructure at a scale. It's the next essential tool in your DevOps toolkit.